Uh, let's start the last session. The last session consists of two online talks by Takashi, Imai, and Natalia Perkins. And to start off, we have Takashi Imai from McMaster University, who would be talking about emergence of spin-polarized domains and spin singlets in Kagome Heisenberg antiferromagnets. So Takashi, it's 35 plus 5. I'll give you a warning at 35.
Yep.
Okay, so over to you.
Thank you very much. First of all, I'd like to thank the organizers for giving me this opportunity to give a presentation of our talk. A couple of years ago, when I first heard about this from the organizer, I was excited because I've never been to India yet. So it's a shame that I end up doing this remotely, but I hope that someday I'll have opportunity to visit India for the first time. So I'm going to talk mostly about Kagome lattice. Time permitting, I mentioned a few words about TIFR lattice towards the end of the talk. So this is the primary three-way collaboration work based on work by my PhD students, Jerry Wan from Toronto and Wei-Shi Yang from Beijing. And we got materials from Yansan Lee's group at Stanford. And we have been collaborating also with my former student, Philip Schinger, who advised us about initially about the ILT, inverse Laplace transform. So two of the key results are summarized in this slide. So we will show you that Zn-barlowite, which is known to be the least disordered Kagome lattice material that does not undergo narrow order, has two distinct peaks. One main peak, this region with spin-liquid-like behavior. But as it turns out, about 60% of Zn-barlowite is showing behavior with negative night shift and enhanced relaxation light, which shows very similar behavior as the antiferromagnetic parent material barlowite. And then towards the end of the talk, I'll show you that we can also see the emergence of spin singlet based on a direct probe using kappa NQR, as shown here. So there are two different types of kappa sites. So Zn-barlowite consists of Kagome layer shown here, which is a corner sharing triangle. Red ball shows kappa 2+, gray shows OH minus. Flowing is green, and the blue is bromine, and then zinc site is light blue. So if you have all of these zinc sites occupied by additional kappa 2+ ion, then it's a barlowite with neo temperature of 15 Kelvin. But you can replace almost all of the interlayer kappa sites with zinc, as shown here, after about 95%. And then it becomes almost isolated two-dimensional Kagome layers, sandwiching bromine, zinc, and flowing sites. So flowing sites coupled with 6 nearest neighbor kappa sites here and one more layer. So overall, 12 kappa sites nearest neighbor are probed by flowing NMR. And it's very good probe to probe the local spin susceptibility. On the other hand, as I mentioned earlier, kappa NQR is the most direct probe if you see spin singlets. And then bromine has a unique property of very large quadrupole moment. So we can probe the lattice dynamics using bromine. So our technique is NMR, nuclear magnetic resonance. And as you know, NMR is the underlying technique for magnetic resonance imaging, which has spatial resolution about 1 millimeter or so. So it's a routine technique now used by medical doctors in hospitals, but you don't really have angstrom size spatial resolution. But nonetheless, when we use NMR technique for quantum materials research, we can measure the local spin susceptibility and its distribution in the form of NMR spectrum or distribution of night shift. And also NMR relaxation rate, when analyzed properly with inverse Laplace transform, can probe the low energy spin excitations and its distribution. Now, as for the night shift or local spin susceptibility, here is what we do. So we apply external magnetic field to the ensemble of nuclear spin, then that results in resonance behavior. So we can detect resonance absorption of radio frequency waves in the form of, so omega naught is a frequency that's given by this. But when we apply external magnetic field, we are also polarizing electron spins. And the polarization is proportional to spin susceptibility. And then in turn, this polarized magnetic moment has interaction with adjacent nuclear spin and exerts hyperfine magnetic field, which is shown as H here. But this H can be both positive and negative depending on how hyper interaction takes place. So altogether, you have external magnetic field and then the positive or negative hyperfine field seen by nuclear spin. So the resonance frequency is shifted by the influence of polarized electron spin according to this hyperfine field. So we can measure by observing the resonance frequency. In effect, we are probing this plus or minus hyperfine field, which results in change of the frequency. That's called NMR frequency shift, also known as Knight shift. So this Knight shift probes the local spin susceptibility with proportionality constant of hyperfine coupling that describes the strength of this interaction in between. It's a nuclear property with a very small temperature independent background term, chemical shift. So here is the example, the experimental data of flowing NMR line shapes for zinc 0.95 Zn-barlowite. So if there was no hyperfine interaction between electron spin, this dashed line shows where we expect to observe NMR line shape spectrum, its peak. But it starts from positive side at room temperature and nearby, and then it shifts to somewhat higher frequency and then comes back down. So if we define the NMR Knight shift at the peak, then the result would look like this. And our results are similar to earlier report from IOP or Okayama University. And so it grows and then decreases towards zero. But we found that the uncertainties are so large at low temperatures, as you can see, the line broadening is bigger than the overall shift. So it's really difficult to nail the exact temperature dependence. And we can't exclude, for example, gapless spin liquid behavior that's expected to show T-linear behavior, for example. Although IOP group fitted this with the activation form and concluded the spin 1/2 excitations with a gap. But we wouldn't go that far. Another important point to note is, as you can see, Bach susceptibility grows toward base temperature. That's when NMR line broadens tremendously. So something else is happening. And as you can see, actually, broadened line accounts for most of the line shape. So if you just look at the peak frequency, that's overlooking something else. And related to that, notice that this line broadening is stretching the overall spectrum to the negative frequency side, which means there's negative hyperfine field and negative Knight shift in this region. So another property we can measure, as I mentioned earlier, is a spin-lattice relaxation rate 1/T1. And 1/T1 in general probes the autocorrelation function of the fluctuations of the hyperfine magnetic field at the NMR resonance frequency we use to detect the signal. Now, in the context of magnetism, one can rewrite this according to Morier and the company later on. So 1/T1 is proportional to temperature times Q summation in the first Brillouin zone of the hyperfine form factor squared times the imaginary part of dynamic electron susceptibility at NMR frequency. So we can probe the spin fluctuation susceptibility using 1/T1. And also for neutron scalars, this chi double prime over omega times T, we are in a low energy limit. So that's nothing but the dynamical structure factor. So in a way, we are basically measuring in the form of 1/T1 Q integral of dynamical structure factor with some weighting factor by form factor, which is Q dependent. So in practice, what we do is we apply external magnetic field through the ensemble of nuclear spin and achieve thermal equilibrium. And then we invert the population by applying inversion pulse. And then eventually, so this is a negative spin temperature situation. And then eventually relaxation results in, so the nuclear spin ensemble going back to the original thermal equilibrium. So we apply 180-degree inversion pulse to achieve inverted state. And then we apply 180-degree spin echo sequence, and then observe the nuclear spin ensemble magnetization. So this is a nuclear magnetization. So it's negative when we do this measurement successfully very quickly after inversion. But if we wait long enough, then eventually inverted nuclear magnetization goes back to the positive side. So eventually negative magnetization goes up to positive if you wait long enough, time t. So if we keep monitoring the intensity of the spin echo signal, then it starts from negative to positive maximum value as a function of the delay time over here. So if we fit G, this is hindering my view here. If we fit this magnetization to a single exponential function, we can experimentally determine the relaxation rate 1 over T1. So that's the ideal situation to happen. And in the case of fluorine NMR and Zn-barlowite, we do see this single exponential recovery around room temperature. However, as is the case often for the spin liquid, approximate spin liquid materials, the materials tend to be really disordered. So most of the model materials of quantum spin liquids, they either show long range order at low temperatures, or if materials do not undergo long range order, they tend to be disordered. And Zn-barlowite does have disorder because 5% of the zinc side is replaced by copper side. So relaxation rate shows distribution. As you can see, it's more stretched relaxation. So traditionally or conventionally in the so-called fluctuating magnetism research field and beyond, it's conventional to fit this recovery curve MT using stretched exponential function with exponent beta. So if there's no distribution, then beta should be about 1, very close to 1. But if you have distribution because magnetism is distributed throughout the sample, then beta becomes smaller than 1 as shown here. So that's how people have been investigating fluctuating magnetism over the years. But actually, one can do much better than this. So we are going to use inverse Laplace transform, the technique which we learned from my former student, Philip Singer, and my PhD students, Jerry Wan and Wei-Shi Wan, developed in-house code because the code Philip Singer had was proprietary to his former employer, a private company. So we couldn't have access to the software. So my students had to learn the mathematical background and then develop our in-house code. So this is how we do. So instead of fitting to stretched exponential, we now only assume that, so we measure nuclear magnetization as a function of delay time, and then we assume that it's a summation of single exponentials without any stretching, but different values of 1 over T1. So we now assume multiple values of 1 over T1 is contributing to the overall recovery with probability P. And this E is the experimental noise. So this is just uncontrollable noise. We can do signal averaging to minimize this, and then we measure this. And then we want to deduce this distribution function, P, density distribution. So to do that, we need to use a technique called Tikhonov regularization. So long story short, so this is already described in many some review articles as well as in Philip paper. So what we do is basically we minimize the right-hand side of this to determine the value of P using this regularization parameter alpha. And then, so here is the example, how it works. So here I'm showing a model data. So these black dots are model data are generated by assuming 2 distinct relaxation. So 1 over T1 3-second inverse and 1 over T1 1-second inverse with overall weight of 2/3 and 1/3. And then with artificially created 0.1% random noise. So these black dots are such artificially created data. So as I said, traditionally people used to fit this with the stretched exponential. And if you do that, actually if it looks pretty good, this red curve is a stretched exponential. So it looks good enough. So experimenters used to say, okay, 1 over T1 is 1.44 second inverse instead of 1 and 3. And then beta is about 0.89. It's close enough to 1. So distribution is not that bad. That's what people used to say. But that's no longer a valid assertion because ILT works. So in reality, as I said, 1 over T1 has bimodal distribution at 1 second inverse and then 3 second inverse with relative weight set by this prefactor 1 versus 2. And if we do the inverse Laplace transform analysis for this artificial data, and then we get this blue curve. So indeed, we can show that 1 over T1 has two distinct components at 1 second inverse and 3 second inverse. And the integral of this peak and this peak, the ratio is proper 2 versus 1. And also, as it turns out, empirically, the center of gravity of this blue curve tends to be close to stretched exponential result. So stretched exponential result can completely overlook important physics if there are multiple components of peculiar distribution in 1 over T1. But nonetheless, at least center of gravity of the distribution may be provable by stretched fit. But until you know you conduct a stretched fit analysis, you never know if your stretched fit analysis is correct or not. Now, the reason we have this finite width instead of delta function distribution is we are using this Tikhonov regularization. So this is basically a smoothing algorithm. So here's an example. So this time I'm showing real stretched exponential recovery. So this is a man-made recovery curve with stretched exponent, and then 0.1% random noise, and then we do ILT. Now, if we use alpha is equal to 0 Tikhonov regularization parameter, then we get this spiky result. On the other hand, if we use very large alpha, then smoothing is too large, so we get just a big chunk. But if we properly optimize based on our code, then alpha is very small but finite, and then it shows this kind of distribution function. So actually, this is basically the shape expected, assumed for the stretched exponential fit. Now, so here is the real life comparison of the data for flowing NMR in Zn-barlowite. So if we measure 1 over T1 based on stretched fit, and then it smoothly decreases and begins to dive below about 50K across lattice freezing, I'm going to show next page. And then beta is close to 1 near room temperature, as I mentioned earlier, and then it develops distribution. So this is all you can say based on conventional stretched fit analysis. But by doing ILT, we can see the actual form of distribution. And as you can see, at high temperatures, distribution is small. And then at lower temperatures, distribution develops a high 1 over T1 tail. So it shows that the relaxation rate begins to develop some peculiar high relaxation rate component, but we couldn't figure this out, the origin of it in a Nature Physics paper published last year. Now, as for this lattice freezing region I mentioned earlier, so we did Br NQR in this region in detail, and I don't have the time to go into details, but it's already reported in PRL earlier this year. So bromine relaxation rate blows up below J, so J is about 160 Kelvin. And if you go low enough temperature, then this divergence is suppressed. So in this region, signal actually disappears. You can't even detect bromine NQR signal. But when the signal re-emerges, this line shape at high temperature becomes very blurred. So this implies that the electric field gradient that sets the NQR frequency at bromine site has developed a lot of distributions or disorder across this temperature range. And also, I don't have the time to go into the details, but the spin echo decay shows peculiar oscillation due to the indirect nuclear spin-spin coupling, which is basically the foundation for RK-KY interaction in the context of S-electron impurity spin system. Actually, RK is an indirect nuclear spin coupling for NMR, Woodham and Kittel. So this is generally the consequence of a structured dimer formation. So between two bromines, there is some kind of dimer for about significant fraction of the bromine sites. So that's happening in this temperature region. Anyway, so if we summarize what we have seen so far, so by measuring the NMR line shape spectrum and the peak frequency, we can determine the NMR Knight shift, but there's peculiar distribution developing at low temperatures where lattice is frozen and also back susceptibility blows up. In the region, something else is happening, a negative Knight shift component is emerging, but we couldn't tell what it was. IOP group didn't say anything about it. And then we did ILT assisted TIFR measurement and deduced the distribution function relaxation rate, and we figured out there's very large relaxation component somewhere in the sample, but we couldn't tell what it was. So notice that basically we were doing one-dimensional NMR measurements for frequency and 1/T1 separately, and we didn't correlate them because frankly, we didn't know what to do. But my students invented a new two-dimensional NMR technique, which I'm going to describe. So we are going to now measure the correlation between the Knight shift and 1/T1. In other words, Knight shift or frequency is the local spin susceptibility distribution, and we can also deduce a distribution 1/T1. So we are going to correlate them. So here is how we do this novel two-dimensional NMR technique to deduce a correlation function between NMR frequency or Knight shift versus low energy spin excitations measured in the form of 1/T1. So here is the NMR line shape. So this is the same line shape I showed earlier. So that's the, line shape measured at 30K. It's the same line shape. And then previously, we measured 1/T1 at 30K here at this peak frequency only. So we were content with it because that's the only thing we knew how to do. But now instead of just doing 1/T1 measurement at a peak, we now measure 1/T1 at a whole bunch of places within the broadened line shape. And then we conduct ILT and deduce distribution at each separate frequency. So here is ILT result. At the peak, we see ILT. So this curve is now flipped horizontally. So this is a relaxation rate axis, and this is a density distribution axis. So at 30K, 1/T1 is peaked around 30-second inverse. Okay, so if you come down here, there's a curve here. So that's ILT results of distribution function 1/T1, and it's peaked around 30-second inverse. But now we repeat the same thing if you measure here, and then this is a relaxation distribution. It turns out that distribution, 1/T1 distribution centered around a much higher value. So in this region, relaxation rate is much greater. So we repeat this all the frequencies, and then we can generate now the two-dimensional contour map as shown here. So horizontal axis shows the NMR frequency distribution, or equivalently distribution of the local spin susceptibility measured in the form of hyperfine field distribution or Knight shift. Vertical axis here is NMR relaxation rate 1/T1. So we generated this based on these curves. Now you can see that in the central peak region, there's a nice oval. So this is the main peak. So Knight shift is set around here. So it's small positive value and relaxation rate about 30-second inverse. So this is the main peak, but there's additional component emerging here at low temperature centered around here. So Knight shift is actually negative for this component, and relaxation rate is almost order of magnitude faster for this component. So basically, this is a two-dimensional correlation function between frequency and 1/T1. The vertical slice is ILT curve, and the integral of this whole thing is the total NMR line shape. But we can also slice this column up horizontally. Then, for example, at the center peak region, NMR line shape is indeed peaked around the same frequency as this one, but this component is suppressed because we are picking up only nuclear spins relaxing at like 30-second inverse. That's this green curve. But if you slice this line shape over here instead, it's only picking up fast 1/T1 component of nuclear spins. So Knight shift is actually much smaller and negative, peaked around here. So there are two distinct components. So we want to adapt this as ILT T1 dissolved NMR line shapes. And my students are very excited to invent this new technique. So here is a summary of the temperature evolution of the color map, two-dimensional correlation function. Horizontal axis is a local hyperfine field. Vertical axis is basically low energy excitations. At high temperature, there's only a single term. With decreasing temperature, new side split of peak emerges with much larger relaxation rate. So distinct low temperature component emerges at low temperatures. So we can reproduce this behavior by assuming, as it turns out, assuming that there are two distinct two-dimensional Gaussian functions. One is peaked around here, and another is peaked over here. So we assume we fit data with double Gaussian to deduce the central frequency of this component and this component, and then central 1/T1 of this component and also this faster component by deconvoluting this overall two-dimensional, actually this three-dimensional data now. So we measure NMR relaxation rate of the main component and the split of peak separately using this technique. And here is a summary. So as I said earlier, so peak night shift is only a small part of the story. When bulk susceptibility blows up, there's negative hyperfine field because of this big polarization in some parts of the sample. So the night shift of that component goes to negative. And then the volume fraction of those nuclear spins of flowing actually reaches as much as 60%. So 60% of the volume in Zn-barlowite is doing something else other than this behavior. So it's not behaving at all like what one would expect for pure, pristine Kagome quantum spin liquid. And of course, we can also deduce 1/T1 of this first component. It's about 100-second inverse. It's very different from the main peak or bulk average deduced by stretched FET. Now, as for this negative night shift, this is not the first time we see something like this. So actually, we saw something very similar when we did a single crystal NMR at the deuterium site and oxygen site in Harvard-Smith site. In Harvard-Smith site, this zinc site is replaced by interlayer copper defect spin by 15% probability. So we can separately detect NMR line shape peak from this nearest neighbor oxygen site and nearest neighbor deuterium site. And they show big negative night shift. So by measuring the night shift of this separate peak, we were able to probe the region in this region, but we couldn't figure out how spatially stretching this effect of the interlayer copper 2+ defect spin was, because both oxygen NMR and deuterium NMR suffer from intrinsic line splitting because of nuclear quadrupole interaction. But the beauty of fluorine NMR is it's nuclear spin 1/2, and there's no nuclear quadrupole interaction. So we can always see just one single peak. So it's more advantageous to investigate the influence of the interlayer defect sites. So to summarize what we have seen, there are two distinct components. One component has big negative night shift and very enhanced relaxation rate because of the interlayer defect we speculated. So we decided to nail this by investigating the parent compound Zn-barlowite. So now we have 100% cup occupying the zinc site, and it's a nail ordered sample below 15K, and we repeat the same measurement. And then again, light shift has a positive value near room temperature, and then it crosses over to negative side and shows similar line broadening when night shift becomes negative. But on the other hand, 1/T1 doesn't show significant distribution beyond what it used to be at near room temperature. There are no additional distinct component emerging in this region. Basically, there's only one component. So if we compare, so we can also fit this, and we can now compare Zn-barlowite, antiferromagnetic Zn-barlowite in blue symbol. So previously, first component of Zn-barlowite was like this, going to negative night shift. We see very, very similar result for the fluorine NMR in antiferromagnetic Zn-barlowite as expected. So this is due to the influence of the interlayer defect site. And also a relaxation rate of the first component is asymptotes to high temperature value of the antiferromagnetic Barrowite. So it's very enhanced relaxation rate. Barrowite shows divergent behavior at 15 K because of critical slowing down. And actually short range order begins already slightly below room temperature. So to conclude, about 60% of flowing sites in Zn-barlowite turns out to show similar behavior as barrowite, antiferromagnet, in the region near the kappa defect occupying the zinc site. So in this diagram, there are 20 zinc sites, light blue. So one of the 20 zinc sites is replaced by kappa defect spin, according to Stanford group. So in this field of view, we have 5% defect, and then we have 60% of flowing sites affected, shown in this orange region. And so we suspect, we propose, basically we are generating kappa defect is generating spin polarized domain in this region. And the fact that the fraction of the first component grows, just to remind you, the first component grows to up to 60% with decreasing temperature, because basically spatially this domain is growing with decreasing temperature. And in this region, basically you can't expect canonical spin liquid behavior because these guys are doing something else. So if we want to see what kappa sites are really doing, we need to probe this leftover region outside this domain for the remaining 40% volume. Now, then we can actually use kappa NQR. It's the most direct probe of the kappa electron spin in the material. So it's known that if you have exchange interaction, 1 over T1 goes like this, according to Moria's high temperature Gaussian approximation. And it turns out that for kappa 2 plus low dimension antiferromagnet, it's always as fast as like 1,000 to 10,000 second inverse. For example, 2-leg spin ladder, it's several thousand second inverse at high temperatures. And this is the Chesley-Sutherland lattice. Again, the relaxation rate even exceeds 10,000 second inverse. It's very, very large because of spin fluctuations at kappa spin seen directly by kappa nuclear spin, because nuclear spin is here, kappa electron spin there, and it's fluctuating, so it relaxes nuclear spin a lot. That's why relaxation rate is very big. But once spin singlets are formed, then relaxation rate dives, and then it goes to as little as 10 second inverse or less. So we did also kappa NQR for Harvard-Smith site more than a decade ago, and actually we ended up suggesting that this is a gapless spin liquid based on stretch fed 1 over T1 measurement, because it looked like power law. And so in some theoretical models, it implies it may be gapless spin liquid. And more recently, also a group also did the auction NMR for Harvard-Smith site, and they claimed also gapless spin liquid because 1 over T1, according to them, is power law, although we didn't observe such behavior. So, but this is stretch fed. And as I emphasized earlier, it's very dangerous. Stretch fit results, if you see, you have to question, did you try ILT? And if you did ILT, what kind of distribution did you see? We also did see Zn-barlowite stretch fit measurement, and it doesn't look like activation form expected for spin singlet. Then it should go something like this, to very small value. But it doesn't show that kind of behavior, or this doesn't show power law behavior either. So it doesn't look like purely gapped or purely gapless spin liquid at all. But now we can do ILT. So here is ILT result summary. So at high temperature, 1 over T1 is centered around one big value, about 1,000 second inverse, which is normal for the kappa 2 plus site. But with decreasing temperature, this main peak is always there. So some nuclear spins at kappa site always has 1 over T1 roughly constant. But the spectral weight decreases, and then a new term gradually appears with smaller and smaller value 1 over T1. It goes down to as little as like 20 second inverse. So this is a signature of spin singlet. So 1 over T1 very small, and then it just splits off instead of uniformly relaxation rate shifting down. So there are bimodal distribution in this case. So stretch fit, these crosses, and center of gravity of this distribution shown by red ball here. Center of gravity keeps track with stretched fit miraculously. However, in reality, these measurements are very misleading. You have to look into ILT, and then spin singlet term emerges to show very low relaxation rate because spins are dying. But there's high 1/T1 component remaining even at low temperatures. So 1/T1 is roughly temperature independent.
So Takashi, we
So,
are at 35 minutes.
okay. So we see something, I'm almost done. So we see something very similar for Hubbard-Smithite as well. And we can estimate the spin singlet by fitting double Gaussian. And this is the upper bound. I emphasize this is the upper bound of spin singlet reaching up to about 50% of the sample volume at low temperatures. So to summarize what we have seen, both flowing NMR, so I just remind you, fast component flowing has roughly temperature independent relaxation rate with big negative night shift. So that temperature independent component is also seen here. So because of the interlayer defect and perhaps lattice distortion is induced in the surrounding area, perhaps that might also induce the enhanced Jarshin-Skimoria interaction and so on. This region is not behaving as purely Kagome Heisenberg model behavior. There's a lot of spin polarization and also low energy spin excitations that results in 1/T1 constant, and spin singlets are forming outside. So we can measure the volume of this. Earlier I showed parametric volume fraction. So what I'm showing here is 1 minus F para, which means basically as a function of temperature, this is the maximum volume where we can expect to see spin singlets. And this is the upper bound of spin singlet fraction. This can be easily be factored to overestimated. So the results are consistent. And if you do the action NMR night shift, if you have X% of copper sites involved in singlet, and then remaining and corresponding X% oxygen sites also should show spin singlet behavior. So that explains why the peak night shift dives activation form. And actually, the OSE group papers, they don't emphasize it, but what's that called D2 site also show activation form behavior. But flowing sites probing the average of 12 nearest neighbor copper sites, so they don't necessarily show activation form. All right, I don't have the time to talk about K-type lattice, but next speaker probably will talk about it. And something not exactly the same, but two-component behavior also often shows up in highly disordered K-type lattice. So again, you need to be very careful when you interpret NMR data. Thank you very much for your attention.
Thank you, Takashi, for the nice talk. Questions. So, is there a question online before I get to Fabrice? Yeah, Natalia, please go ahead.
Can you hear me? So thanks a lot
Yep.
for a very interesting talk. So I have two small questions. So the first question, I didn't quite understand this polarized domain. Can you say something about this structure? I mean, is it, I think the only thing what you were saying about the size of this domain, if I just the volume fraction. But can you say something more precise what is inside this domain?
We can't tell exactly what kind of magnetization is induced in the domain, unfortunately. Basically, we see one big broad blob. But one thing we can say is there's both a positive night shift distribution, negative night shift distribution. So that means basically magnetization induced in Kagome plane maybe even oscillately. However, unlike the case, so if you remember what happened for like copper oxides, then you can have oscillatory spin up, down, decaying exponentially. But in our case, Kagome plane is fluctuated. So you can have that sort of simple up-down configuration. That's why I'm drawing a 120-degree structure locally here.
Yeah,
so what I'm imagining is, so what I'm imagining is there's big interaction between defect spin at the nearest neighbor site. And then this guy will have exchange interaction with the second nearest neighbor, but it's fluctuated. So it quickly decays. And then outside this region, basically effect wanes. So that's sort of speculation, but that's all we can say.
And second question, very quick. So can you use MUSA just to have some better idea about what's going on in these regions?
I think if they also do ILT analysis for their relaxation rate, they should be able to get basically the same results. Okay. Night shift they measure is basically the same thing as flowing side. So I doubt MUSA, I know where your question is coming from, but it's probably basically the same information.
Okay. Thank you very much.
Fabrice.
Yes, thank you, Takashi, for the nice talk. So just one comment and maybe one question. So you mentioned that we didn't measure the T1 with a stretch exponential. Actually, that's not correct. We measured in the NMR shape, in the NMR line shape, we measured far from the defect, and we measured the T1 with just a sum of exponential without a stretch and without change of the shape of the relaxation with temperature. And then I think we get rather similar results to you for the component that doesn't evolve much with temperature. And
any agreement would be good.
And one question maybe, just to be sure, how did you measure this volume fraction and how it evolves with temperature, this 60% volume fraction?
Oh, so basically we are deconvoluting this into two pieces, so there are two terms. So one peak is always around here. Actually, this doesn't broaden too much even at low temperatures. And then there's additional components. So we have basically one Gaussian centered around here, another Gaussian centered around here, which is moving away to negative side. So we can integrate two separate components in two-dimensional parameter space. So based on the integral, we are estimating G component, first component, second component. That corresponds to G, this component and this component. And this component is reaching as much as 60%.
Okay, yes. It's more or less, yeah, it's evolving a little bit with temperature, okay.
So we can't really resolve it. So the problem is in this region, basically this peak has finite widths, both horizontal axis, frequency axis, and also relaxation rate. We can resolve only as much based on ILT because of signal to noise issue. So we can't resolve this peak. So this peak is merging into main peak at high temperatures, and we can't resolve. But I do think actually small component of this is persisting in this region as well, but we just can't do quantitative analysis. Well, unless my student spends like 1,000 hours averaging a signal to kill the entire noise, then maybe we can deduce a fraction at high temperatures, but they have to graduate.
Okay, thank you.
Okay, any quick question? Okay.
Just a quick question here. So I'm wondering, I guess you also measure T2, right? Is this affecting your fraction, or, I mean, do you have this under control? How long are T2s?
For flowing side, T2 is very long. So volume fraction estimation doesn't really affect. On the other hand, for copper side, it's really fast. And it looks like there's a curvature like this. So we can't really extrapolate to tau is equal to 0. That's why we keep saying conservatively. So our estimation of the spin-singlet volume fraction is upper bound. There's no doubt about it because basically we can't do the T2 correction in a proper way. So this is the upper bound.
Okay, thank you.
Okay, so we'd like to move on. Thank you, Takashi, for the
Thank you very
talk.
much.
And hopefully we can have you here in person the next time in near future. Okay.
Sure.